This whole section deals with the properties of logarithms, and we use these all over the place in calculus to simplify stuff, and to simplify formulas, and to simplify things that we can use a calculus process on. So these are essentially attached to the properties of exponents. They have to be, because remember, the relationship between the logarithm and the exponential is that we have the domain, we have the range, and the exponential function b to the x takes x values in the domain to y values in the range. And the logarithmic function, log base b, picks up range values and returns it to domain values. So in the domain, we have operating the properties of exponents. So these things work here. That means if I want to use the inverse function, there's got to be something that's related to the property of exponents that has the same type of configuration that operate on this side. And what operates on this side will be the properties of logarithms, the properties of logs, so that one has to interrelate with the other. With that being the case, that means that when I'm looking at the properties of logarithms, I'm really looking at some form of the properties of exponents. So they have to work in conjunction with one another. Now, we had talked about the logarithm and the exponential function being inverses of each other. One of the properties of logarithms is called, or one of the properties is called the inverse property. Now, what this is, if I know that the exponential goes from the domain to the range, the log goes back from the domain to the range, log goes back from the range back to the domain. This guy here is the inverse function. This is the regular function. And so what we've done is we've taken the regular function, which in this case is f of x being equal to a to the x, and we've stuffed the logarithm function inside. So what this really is f of f inverse of m, in this particular case because the letter is m, and the inverse function is going to be log base a of x. So this says into the regular function I'm going to stuff the inverse, and we know what happens is the inverse and the regular function take each other out, and what you're left with is m. That's why it's called the inverse property, because what you're doing is it's the composite of the regular function and the inverse. This guy we don't use quite so much. We do use this guy oftentimes in higher levels to solve equations. Here we kind of skirt it, and even in calculus we kind of skirt it, that we're using the inverse property because we do it in other ways. Now here, if you take a look, there's the original function, and the outside function is the inverse. So what this really is f inverse of, and I stuffed the original function, in this case it's r. And we know that the function and its inverse take each other out, and you're just left with r. This one we use much more frequently. So it's the inverse properties of logarithms. The big properties that we're going to be using, and these are the big four, and they relate to the properties of exponents. It says log base a of a product is a sum, log base a of m plus log base a of n. And what it's related to is this property of exponents is a to the m times a to the n is equal to a to the m plus n. Remember, the logarithm is an exponent. Here I'm adding two exponents, and this becomes the product. So a product turns into the sum of the exponents. So that's the property it's related to. This one is log base a of m divided by n, and you're going to subtract the two logarithms. The log of the numerator, subtract the log of the denominator. It's related to this property of exponents. It says that a to the m over a to the n is equal to a to the m subtract n. Again, I'm subtracting two exponents. The logarithm is an exponent, and so you're subtracting the two exponents. This one's much harder to see. It's that log base a of m to the r is equal to r log base a of m, and it's related to the one that says that a to the m, and in this case to the r, is equal to a to the m multiplied times r. And in this particular instance, there's an exponent. R is an exponent. It's the product of two exponents. Much, much harder to see. Additional properties is that log base a of a is 1, and this is because a to the 1 equals a. And all I did was rewrite this in exponential notation. And log base a of 1 is 0, and that's going to be because that a to the 0 equals 1. And again, I just rewrote this in exponential notation. So it's directly related to the properties of exponents, as it should be. As it should be. Now, when you're working with the properties of logarithms, you could care less about saying, oh, this is how it's related to the properties of exponents. You tend to work with the properties, and then you remember the properties, you use the properties, and don't even think about the fact that they're related to the properties of exponents, the properties of logs. It's kind of like the properties of radicals. You don't think about them being related to exponents unless you have to.